Already the title may cause you sleepless nights. Yeah? Semigroups, and that's even short because what I will only tell about are strongly continuous semigroups. A group is an algebraic object. A semigroup also. We are not doing algebra, we are more doing in the analysis. And then you have more to talk about strongly continuous semigroups, which is really a separate section. If you look in the literature on semigroups, then you get all kind of algebraic things, yeah, where you don't understand anything of. I don't want to do this. So here we have this math theory, semigroup. What is the whole aim? The whole aim is that I want to study the solution map. So I have my PDE and I'm wondering what is my solution map. And the solution map is basically the map that gives you from the initial condition to the solution at time t. And therefore the whole range of t. Yeah? That's the solution map. I start finite dimensional. So, A is just a matrix, and then we have all learned that the solution is given by this. E to the power AT times the initial state. So x0 is just in Rn. So this E to the power AT is then the solution map. Yeah, it maps the initial state into the state at time t. Let me just leave that last line for a moment. It's just the following that I want to say. So if you have this, doesn't matter if A is 1,000 by 1,000 or 1,000,000 by 1,000,000, I know this solution exists and will be given like this. Yeah? So existence is no problem, you would say. Yeah? Finite dimensional existence is no problem. Calculation is, if this matrix is 1,000,000 by 1,000,000, you don't calculate this thing anymore. Even by a 10 by 10, it gets already tricky to calculate it. 4 by 4 is the last one you can really do symbolically. I think Mathematica can do for you. 5 by 4 is already impossible. Just to do it. That you cannot explicitly write down the roots of the 5 type of the determinant of the fifth order.
It depends on the matrix.
Depends on the matrix. If the matrix is 0, I can even or 1,000,000 by 1,000,000 write the solution down. Yeah. In general, the answer is as soon as it gets a little bit realistic, say you have a large state, then you can only solve this via the computer, approximately. Yeah? So even existence is no problem. Writing down the solution by hand, you do it once in your exam, if you have this, for a 2 by 2. And maybe if your teacher doesn't like you, he gives you a 3 by 3. And there it ends, yeah? That is good to realize, eh? that this, and this is even, there is already a famous paper. And it was something like 25 dubious way of calculating the exponential of a matrix. It was something like that called. And I can't find the exact title, but it was something like that. So every way, so you learn probably by e to the power at, just make this Taylor series. Yeah? Identity plus at plus a squared. For a 10 by 10 this already goes completely the wrong way. Calculating eigenvalues, eigenvectors goes completely the wrong way. Basically they show all the things which are known in mathematics that this will lead to a very bad approximation of e to the power at. Yeah? So you really need numerical techniques, not just a mathematical proof, but you really need original numerical techniques to solve this, to solve this basically. And that never goes by calculating the exponential. So existence is clear, calculation, different story. Let's put it like that, yeah? So, okay, we denote this map by t of t. So we don't write e to the power at anymore, we write capital T.
So if we try to approximate the eigenvalues of A, we don't get a good approximation for a solution mapping.
Depends really on your matrix. Calculation of the eigenvalues is already a tricky problem. If A is a normal matrix, then that is quite reliable.
Okay.
Yeah? But not for every matrix. That is basically.
Okay, if we have generalized eigenvectors.
Yeah. Then, or not.
Yeah, or not, yeah.
Yeah, that is very hard to distinguish if you have them or don't have them.
Okay.
Yeah? And suppose you have 100 by 100 Jordan block. So your characteristic polynomial looks like this. If you know this, then you know and that it will be 0 in that multiplicity 100. But if you plot this, if you don't have any idea what the function is, you just plot the characteristic polynomial, after a circle of 1/10, you already see 0. And then you have a circle around 0 with a radius of 1/10, where the zeros could be, because you don't see it anymore. Yeah? You see the problem? Just you have numerically to decide where am I, and then if you have something like this, you have no idea. Treverton is the name really of that, and spectral radius and things like that. There's a whole, I also have nice books about that, beautiful. Nice theory is that as well. But we are here, yeah? So my problem is just, the general rule is, okay, don't worry about it too much, but it can be problems. So the implementation in MATLAB, there is really thought of how do I calculate an exponential. Yeah? It's not something you just program out of your hand and just do it. You just have to be careful. Okay. Now I do the other opposite. I just think of an equation that I have, say a states equation, x dot equals something, and I assume myself, I think, and let's think I have already my solution map. Yeah? So I have my solution map, which is already strange, I don't even have given an equation, but I think, suppose I'm lucky, after 5 years of work, and I have my solution map. But what can I say about this solution map? What properties would it have? And now I'm assuming that my differential equation is linear and time invariant. So that means that the coefficients don't depend on time, and that if I plug in x, or 2 times x, I get 2 times the answer. Yeah? That's linearity. Linearity means that constants go in, the sum goes out. And then I just think, okay, so we have this mapping, and this is the solution map. So x0 is mapped onto x of t, and I know that the underlying dynamics is linear and time invariant. And I say tt is linear, because my equation is linear, so if I would start in the sum of 2 initial conditions, I would end up in the sum of the 2 solutions. Yeah, that's precisely what I mean, that this mapping is linear. The original is, the sum of the original is mapped into the sum of the answers. Yeah? So by just thinking that my underlying system is linear, I get somehow by solution map inherits this linearity. Clear or no? More. It's also trivial. What would be my solution at time 0? Okay, I'm still in my initial condition. So I have the identity, yeah? The solution at time 0 is the initial condition. And since it is the mapping from x0 to the solution at time t, it can only be the identity. Yeah, that's just then the way the solution map is defined. Notice. I look, and so I start at time 0. So let's, time 0 is here. Yeah? I start at time 0. First I make a step t2. Oh, I make a step t2, t1. Yeah? A long step. That's basically, you can put here an x0, and that is then the state I would end up in. Yeah? Now I do it the same experiment again. So but I first say, I only go one time step. And then I say I stop, and I say let this be my new state, my new initial state. So I start my old, and then I take my t2 time step. So then I'm here, you see, oh no, here I first did t2 and then t1. But because of the time invariance, that must be the same. The system does not know. Time invariance means that I can always reset every time to 0. The system only knows time when I push the clock, when I say give it an initial condition. There is no clock from itself. Yeah? The time only enters, it's only the time difference that has an influence. That means the time difference between starting and end. So they should be the same. That's the time invariance. I can reset to 0 anytime. Doesn't matter. Now I can just think of my equation. But now I just take a step back and say, hey, this is nice. I don't even know my TT. But just by thinking linear in time invariant, I just have these properties. And the second property I just have because I think of it as a solution there. It's just linear, that follows from the linearity of my underlying equation. This is just because in time 0 I have not really started. This is a time invariance. And this is also called, because time, I only think forward in time. So my t1 and t2 are positive. So I only demand this property for positive t1 and t2. And this is basically called the group property. Yeah, a sum here is set into a product here. Yeah, that is called the group property. But because I only have it for positive time, this is then called the semigroup property. Then you only have it on half the tx basically. Yeah? That's where the name semigroup comes from. So this is a semigroup. But there is still something missing. And then I always say that it takes really smart people to understand what is missing. Yeah? Because you think, oh, there's nothing missing. But there is a missing. What is missing is basically the connection with the underlying space. You say, no, it's there because TT maps X into X. So it's already by definition, it is a mapping of my underlying space. Fine, but my underlying space are functions. It's basically missing the connection with the norm on my space. There's no connection with the norm on my space. And that is, I think, Yoshida introduced this, and this is really clever. Oh, I just go here to the last one. That's basically it. The last property is essential. It brings it basically from an algebraic thing, and just a semigroup, it brings it really to strongly continuous. It makes it, there is a continuity involved. And what does it say? And if you have thought about it, but I haven't thought about it, I didn't want to invent it. It's very clever because a lot of results just come from this collection of properties. Yeah? But what does it say? If I have my solution there, I can look at the solution. This is my solution at time t. Yeah? This is my solution at time t. So I have my solution at time t. I have a nice movie on it on YouTube, and now I drive it backwards. I go backwards in time. What should then happen? And basically what it says, then you should recover your initial condition. Sounds very logical, but okay, it's not in the other properties. Yeah? So basically what it said, if I take my movie backwards in time, I see more and more my initial condition appearing. That's a continuity. Yeah? So it's not something that I see this and this all the time. My initial condition was like this. Yeah? Now if I have this, then I will slowly see that evolving. And that's a continuity. I don't jump I don't make a big jump after my initial condition. Yeah? There has to be somehow smooth, but it could be very rapid, of course. Yeah? But there should somehow be a smooth transition from my initial condition and to the other solution. And this is then the strongly continuity, because it's continuous backwards, okay. It's only continuous from that side, yeah, from the positive side. And it's called strongly because it has to hold for every x0 and not just without the x0.
But this would be in strong.
Okay. The property, okay. They also proved, and you can prove it, and the proof is not so easy, that if you want this without the x0, so the tt becomes the identity, then the A can only be bounded. So you throw away all the partial differential equations. So that's funny. So this is the logical property. And then you can look in, okay, I can bring it tomorrow.
No, I know, but I just wanted to mention that if you leave the x0...
Oh yeah, then it's stronger, then it's uniform, yeah? So it depends on your initial condition, how fast you going to look. If you want that uniform, then that's too strong. That you will not have.
But instead of t that goes to 0, yeah, for example, t2 that is higher of t1 that goes to t1, and you replace x0 of xt1. Does it hold? Yeah. Because you substitute the initial condition with the new xt1.
You can do this. So that you also see in mathematical definitions, they want to have it as little as possible. Yeah?
Okay, so it holds everywhere for everything.
Yeah.
And this is a way of saying
yeah, but you assume it at 0,
okay.
And then your semigroup, because 0 initial time could be anywhere, you get it basically from the positive side automatically, yeah, because that's just there, but you also get it from the other side then. But then you have to prove. That you have to prove. But from the definitions, just combining these two, somehow you know that's true. You get it already for an every point. Yeah? So what is your solution? Yeah? So let's think about that. Your solution in time is basically continuous. That does not mean that in a point it is continuous. But it's in my state space it's continuous. So that means that if I take the difference between the solution here and here, and I let this time go to infinity, to 0, that then the norm of this difference go to 0. Yeah, but it could be that it's, okay, very weird, but normal, okay. If you look at it in the simulation, then you also see it in pointwise, but because that your simulations are more smooth than maybe your weird solution is, yeah? Yeah, but you can have, but okay, basically it's just the difference in norm goes to 0. So that means the integral over the error goes to 0. Okay. That's a strongly continuous semigroup. Now I have here on top, I have something on operators.
In the space it must be.
That's a notation. L of x stands for linear operators from x to x. So linear operator just means this is linear. Yeah? You have the, if you let Q work on the sum of two elements, you just have the sum of the answers. But you also want this. So it's basically linear and bounded. So linearity means this means boundedness. So if there is a universal constant, depending only on my operator, I come to universal constant such that the norm, so how large, so basically what does it tell you? If you just have an arbitrary element of norm 1, and I let Q work on it, this new image could lie anywhere, of course, but it cannot be arbitrarily small, large. Yeah, because if it would be arbitrarily large, then I cannot have this Q there. Yeah?
I was wondering, he has partially answered, but I want to ask as well. Like, when you say that it's continuous in time, I mean, it's continuous when it does like this, but not quantized. It means that in space it's something different?
In space it could be something different.
But where is space there? Is inside x0?
No, it's in the norm.
It's in x0.
So what is it? If I think of L2, yeah, let's think about
Because
L2.
x0 is a function, so inside x0 there is the space.
So I have my solution, say W T zeta. Yeah, and here I have my initial condition.
This is space zeta.
Zeta is space, yeah.
Okay.
Then that last one means that if I take the absolute value, okay, square, okay, you can, if it's real, and I integrate this from A to B, and this goes to 0 if T goes to 0. The error goes, or the distance you could say from my solution to my initial condition. Let's think very logical. I will give you a very simple example. I define my, and now I have a heated bar, and I give it as initial condition, I give it this. Don't tell me how I do it, how I implement this. I know very clever engineers in Eindhoven, they can do this. No, it's just nonsense, of course. Yeah? If I have this, that are my initial condition. Yeah? Then you will see that my solution would look something like this. Something like that, yeah? At time t. And you see if t gets smaller, so this is say at a certain t, but if t gets smaller, it's more and more, looks like this.
But wait, this is a representation A and B are in space.
This is
Right.
zeta. Let me just make it clear. This is zeta, that direction.
Okay.
And this is say, and this is the black one is W0. Zeta.
Okay.
And the blue ones are WT zeta.
For T fixed.
For a T fixed, and then I have another T, and I have here, I have again another
Okay, so
T.
is every one of them is a picture of the system for different T?
Yeah.
This is the fact.
That's the fact, but
and when T goes to 0, the difference between the blue or the red or
Yeah.
something else.
but see what it becomes in this point.
Yeah.
In this point, I basically, you can prove that I'm in the half.
Okay.
So you see at this point, I don't converge.
So if you compute that integral,
This
it
integral,
goes to zero,
zero.
goes to zero.
But at every point, it does not go to zero.
Yeah.
Yeah?
Ah. Yeah. Takes a lot of time, a bit of time to understand.
No.
It's
You already
okay.
get a picture in your mind about these spaces, etc. Yeah?
But the functions, the blue functions don't need to be continuous. They can also be uncontinuous.
Okay, okay.
Yeah. But in the heated process, what happens, and that's why I cannot build it, because I have to have something like this. Heat becomes, and that you can also prove, at least if the heat evolves according to Fourier's law and things like that, then it immediately becomes C infinity.
So for example, if I say, like, if I say that x of t1 is a state,
Yeah.
what I mean really is that the function, the image of the function that I have when I fix a t1, but in space is not fixed.
Correct.
It's like I projected
It's
in one dimension.
like I have. You have here basically space and here time, and this evolves in a certain
And I
way.
projected in just one.
And I just cut it out basically. At a
So where
certain
the
time.
line that at the beginning in the map were
Yeah.
the same.
You could draw a 3D picture if you have space one-dimensional.
Okay.
Ah, yeah, there it is.
It's for
Okay.
convenience.
So we write x is t, but in fact it's x of t and x with t equal to t1, for example, if it's t1.
So and we will get to it later. I don't know how much time. I don't want to take too much time because it has already been a long day. Yeah. But what we will do, basically you will in a PDE you write WT of zeta, yeah? Time, spatial, you just put them nicely as brothers together. Now in this state space system, you basically put somehow space under the carpet, I could say, yeah? You only write x of t.
Okay.
But at a fixed t, it's still a function of space. So then you get this kind of notation that say basically x of t that I can evaluate in a point, yeah, because this is still a function of space, and that was then the old this. So instead of seeing this, basically what happens, instead of seeing this 3D picture as a collection of points, yeah, of two points where I see them now as a collection of lines.
Yeah, it's all layers of
Yeah,
fixed
layers.
lines that you put
Yeah.
together.
0.5,
Okay.
0.15. So
Yeah?
Okay. Yeah.
yeah,
Yeah, because there was a time when there was no space anymore, and so I was wondering.
Yeah.
But it's still there.
It's still there, yeah.
Okay.
that
And we can do that. We just.
we just
Of course.
yeah, the
You have to make clear. But basically that is what I'm saying. If x of t is in L2, L2 is a function that depends on the coordinates still, yeah? So by just saying x2, my state lies in L2, I'm saying, yeah, there is still a spatial coordinate. I don't write it explicitly down, but there's still one there.
Okay.
Yeah?
Sorry,
Yeah?
I
No.
didn't understand. In this case here, the conditional strong continued
Yeah.
continuity. So the limit is exactly the initial condition. So it holds for this example or not?
If you would do it, I'm looking at the heat equation, so I'm
Yeah.
just doing out of my memory what is the solution looking like. I'm not saying, but you could somehow understand it. If I have a heat equation where the diffusion of heat, here I have a certain area of temperature, here I have temperature that it immediately connects. If I really do the looking back and say to what, if I really take my movie back, what do I see appearing? I see here 0 appearing, so let's write it next to it. What do I see? I see this, but I also see this. Here this dot means it had the value, so let's put a coordinate here. here I have basically point C, yeah?
Yeah.
So in point C, it had the value 1. Let's also put values there, yeah? But now, if I take the picture backwards, in the point C, it does not have the value 1 anymore. It has the value 1/2. It's there.
In my solution.
Yeah, if you take the solution back, you look at this picture, and you only concentrate on the point C, then you see, and that happens already quite quickly, you see that this point C is always on 1/2.
Yeah.
And then you say, okay, then in the limit it's also 1/2. But, yeah, if something is always 1/2, if I take a limit, then it's also 1/2. But that is not the original value. So this is really, but if I take the difference of this, of the initial condition, and so if I now take the difference of this black line with this blue line, so this is basically the limit which I get. Huh?
Yeah.
And I take, and this was the black is the initial condition, I take the difference of it. Then I get identically 0 except in one point where it's 1/2. Now how much area is there under one point? 0. Yeah, I have width nothing, I have height 1/2. So this integral is still really 0.
And so still hold this.
Yeah. But the question was, is it also pointwise in space? And it's not. The error is going to 0. That does not imply, okay, most times yes, and things like that, and it really depends on how you define an initial condition, blah, blah, blah. But if you would do simulations and starting with this initial condition, you would see that at the point at C, you are not converging. But if you calculate the error, basically, you are converging to 0. Yeah? So this does not mean pointwise convergence. Not in L2, yeah? If you have another state space, then it can mean it. Also depends on your state space.
Thank you.
So there is an implicit norm that
Yeah. It's this is in the norm of X. I mean, limit is always in a norm, yeah? So it's better, have I did that? No. No. It's almost better to write if you want to have it explicit, which I can now look at it, it's better to write this, Tt x0 minus x0. Then I have the norm, and this goes to 0. The limit of t is 0. And this is now the norm in x, I just write down. Yeah, that is the mathematical definition of this. So in this last property, there is really the connection made with the norm of my state space. And you can have two different state spaces where the solution map is somehow the same and you don't have this. Yeah, the one you have and the other one you don't have. Yeah? Now that's the semigroup, so we are already here. Let's see, because I'm also looking at the watch and I want to stop in a few moments. I think that it will be good enough. Talking already quite long. This is called strong continuity. This is where the name strong continuous comes from. This is the word name. So this was this bullet or this arrow here. This is the semigroup property, yeah? And then this is the strong continuity. That is what I said all the time.